Thanks, Melanie, for this introduction. Welcome, everybody, and also thanks for the invitation to this exciting workshop. The mission at DeepMind we're trying to follow is not very humble, so it's to solve to solve intelligence, and we try.
Can we pause there?
Sorry?
Can we pause there? I mean, everybody looks at this slide and gets to be flipped and laughed. Can we pause there? What does that mean? We're throwing billions of dollars at something. Can we actually
solve intelligence?
What does that mean?
It's understanding intelligence, what intelligence actually means, and we try to do this by building an artificial system that can be called intelligent.
What would that mean for something to be called?
The definition, it's very difficult to exactly define this, but one working hypothesis is there. So the intelligence is the ability to solve. Right.
Every DeepMind talk puts this slide up, but it's just kind of, I mean, it's a little absurd, no?
No, why? So there is an existence proof of intelligence, like us, and we try to build something with a machine that can be called as intelligent as a human being. So that's a very.
Ben is asking whether or not you have a working definition like a Turing test that you would say if we achieve.
Not yet. So the working hypothesis is
the goal, and we'll figure it out at the end.
Yeah, I think we will. We will figure it out along our way. The goal is a bit vague. But it's kind of, I think it's kind of understandable, at least, what intelligence means.
A solution is usually associated with a problem. What is the problem?
I think we want what we want to do. Maybe you can accept the working hypothesis. We want to come up with an artificial agent that is able to solve a wide variety of tasks without being changed. Is this, that's nice?
Why don't you say that?
Okay. Because you interrupted me before I came to my second sentence. Okay.
I disagree with that.
So we have a couple of examples, what we think is going in that direction. So the first one was playing Atari from only pixel with one agent architecture, with one set of hyperparameters. Next thing was to beat Lee Sedol in the Asian strategy game Go, and then pushing this even further by an algorithm that learns to play Go, chess, and Soji even with a minimum amount of prior knowledge or no prior knowledge. And here are some learning curves that you see. So we originally it was a big challenge to be the world championship in Go, world champion in Go at all. So we put in a bit of prior knowledge, like games and examples of good moves. And this was AlphaGo Lee, the red line there, with a certain ELO score. And AlphaZero, a system that just learns out of success and failure, is able to beat this AlphaGo Lee version after only 8 hours of learning. Of course, with a huge compute provided by Google, but I think it's an amazing short time to get to this level of knowledge without any prior knowledge put in at the beginning.
Well, okay, what does that mean?
It just plays against itself, and it's only being told if it won the game at the end.
How does it know what's valid rules?
The rules is only if you choose the wrong actions, you're not going to move forward.
You choose the wrong action.
It doesn't apply. So you're
So
restricted.
that's coded in, though, right?
Yeah.
That's coded in somehow.
It's a simulator.
Yeah. That's basically how the world behaves. How the
Simulation.
Yeah.
In the AlphaZero chess, you don't incorporate the rules of movement for different pieces. Those are learned.
Yeah, those are learned. Yes, you don't encode it in the Monte Carlo tree search that you're applying to learn the overall things.
Computer Darwin.
Yeah, basically, yeah. You learn from scratch.
You don't code in the tree search, but you do code in the values, right? So the values are hard coded.
Sorry?
There's something's encoded.
Something is yeah. For example, if you win the message that you won the game at the end.
But more than that, right? It's like what happens? So if you take a move and it's illegal, something is encoded that you can't do that, right?
Yeah, you can't do that. Yeah.
So that branch dies in the tree search.
Yeah. but only if you actually execute it. So it's not put into the system so that you know in advance, for example, what moves you can do. Yeah? Okay, so a similar learning curve for chess. There humans don't play a role, so it's just beating another computer game, which is Stockfish, after 4 hours, and at the end it wins in 155 to 6 games. Sorry?
How many games did agent play? 8 hours.
In these 4 hours, honestly I don't know. There are millions of games because we use a lot of parallel compute there, but I don't know. It's a lot of real time, corresponding to a lot of real time. Shaba, do you have an idea? Yeah. Hundreds of millions, at least. Yeah. So what would AGI actually mean for control? So the vision that we have is something like that. A human baby that comes to the world and has to make sense of all the sensor streams that it gets from vision, from audio, from haptic information, and has to control the whole body, all the muscles, and kind of make sense of all that. And at the beginning starts to play, interacts with the world, and gets educated, learns to write, learns to calculate, and does proofs and whatsoever. So that's kind of our leading vision that we have. So what we want is to learn from scratch, probably with some, of course, prior knowledge built in, but that should be very, very general so that we can solve a very rich set of tasks in the real world from raw signals, and ideally yet kind of efficient. So I'm heading the control team at DeepMind, and our mission is that we want to do that what classical control normally does. We have a closed control loop with feedback, where in classical control you would try to understand the process and then design the controller accordingly. We try to just learn this by giving it some kind of goal that we usually give in terms of a reward function. The thing here is that this reward function can be very general and very task designed to just specify the task goal. So it's a very general way of specifying what you actually want.
Can I ask you a question?
Yeah.
If you heard my talk yesterday,
Yeah.
you have witnessed that I'm an admirer of AlphaZero.
Yeah.
I think it's a tremendous accomplishment. But how do you think chess and games differ as a domain of a problem domain from what you have here on the board?
I think at the end they don't differ at all. So they could be written in the exactly the same formalism. I think that's the beauty of these Markov decision processes.
I think that's wrong.
Yeah, no, that's
Okay. If you think that there are no differences between games with set rules, with particularities like limited number of move selection, and problems where the dynamics change over time, where there are disturbances, the model is unknown, and so on, I think there's a huge difference between these problem domains.
I agree. I agree. So
They say that you aim towards solving different and more difficult and more complex problems, but they are the same. They're not the same, obviously.
I think it depends on the granularity where you look at those. On a very high viewpoint, they are basically the same. Both in chess and in control, you go for a couple of steps. At the end, you want to reach a certain goal.
If we go to the time of the ancient Greeks, then we would have a very general view of the world, and everything would be sort of more or less the same.
Yeah.
I think perhaps, I mean, this is my biased view, but they're not the same in a very fundamental way, which is that what you don't know in Go is what the opponent will do, right? That's the dynamics part that you're missing. Much like here, you don't know how the physical world works. So in that sense, they seem the same. There's actually a fundamental difference between them because in AlphaGo, when you're in minimax territory, you can assume that the opponent is adversarial when they're not. And that will be okay. You
could model this as a certain type of noise that you have in the process, and then you're again in this very general language of a closed loop control system.
But the world is not.
Sorry?
Clarifying question. Are you going to talk about New Zero?
No, not yet.
But I mean, like, yeah, like you know the dynamics where you're optimizing optimizing against a simulator, that's a difference, that's a big difference, right? And then maybe you talk about simulator and stuff.
Yeah, I will definitely talk about that. Yeah.
Whether you can transfer the results from a simulator, like whether that approach is feasible or viable. So that's like using a lot of compute works really well with simulators. If you are using a lot of compute but you have limited amount of data, maybe that's what Dimitri is also referring to. That seems to be like a fundamentally different problem because now you have to care about.
I completely agree. I completely agree. Yeah.
Just like
I was just
conflict, but there is no conflict.
Yeah. From a very high level view
of robustness.
No, I think the conflict is the rhetoric, man. The conflict is the rhetoric. I mean, at some point you have to be scientific, and I think that's we find that. But I think the science will come eventually. But I think that everything gets conflated with the weird propaganda and lofty goals, and it kind of moves away from what the kind of scientific contributions are. So I think that's the issue everyone's having, which is fine. I mean, it's like I just want to say where we finally want to go and what the vision is, and that these methods kind of aim at solving these kind of problems. Okay, so the scientific contribution will be, I will talk about our viewpoint on how to make reinforcement learning data efficient, because as Csaba also mentioned, so in things like Go or so, we have the good thing that we can do a lot of things or basic everything in simulation. When it comes to control, what we finally want to do, we want to learn on these real systems directly, and then we want to be really data efficient. So we want to learn out of a very few examples that can be done on a real robot, for example, in a couple of days, instead of in a million years or so. And I will talk of how we tackle these kind of problems. Then I will also talk about a couple of advanced aspects, and then I will conclude with a couple of challenges and a wish list that I want to get out of these workshops. So the promise of reinforcement learning, as defined by Sutton and also by the great textbooks by Dimitri Bergsekas, which I used as a basis for my first lectures on reinforcement learning, are that you're giving a stochastic system which follows the Markov property. Then you can give the reward or the target that you want to have in a very general way. For example, if you want to lift something with a robot arm, then you can just specify it's 1 once the object is lifted and 0 otherwise, which finally would give you a time optimal controller. So it's a very general framework that allows for a very simple specification of the goals. And since this is, since we are optimizing the cumulated rewards over time, we can also cope with the dynamical aspects of systems. So if we were talking about this in the previous lecture, if the system actually shows some dynamic behavior, then this can be covered with this kind of approach. The methods, also as Dimitri Bergsekas mentioned yesterday in his talks, are known for a long time. So they're based on value iteration, on dynamic programming principles. And what we are in particular referring to is the model-free variant called Q-learning. Most of the systems that you will see afterwards are handled model-free, because we kind of believe that this will finally lead us to the better policy. Of course, we can also discuss about this later on. And the main point here is that you can approximate this Q function with a neural network and do the value iteration with a neural network. And there are several examples of this, and I will talk about this in the future too. So the challenges for control are in particular that we have continuous states. So this distinguishes it from many games, for example. We have continuous actions. We have a high number of degrees of freedom. So if you think of a robot arm, you have 9 degrees of freedoms. If you think of a humanoid, you have something in the 50 or 100 degrees of freedom. And therefore, this poses a main problem for these reinforcement learning methods, because if you want to see reward or if you want to see the goal, then the search space is actually really huge. So if you have 9 degrees of freedom, 3 actions per degree of freedom, 50 steps, you have more than 10 to the 200 paths. And if reward is sparse, then you can have a very hard time to actually find this reward.
So typical approaches are you go learn in simulation and then bring this learned controller to the real world, or you do learning from demonstration, you actually show it some paths. But what we want to do is actually we want to solve the whole problem ideally, and also find methods to kind of search this tree in a very or in a kind of efficient way. So we want to learn from scratch, and at the same time also data efficiently. So the classical reinforcement learning as proposed by Sutton acts basically as incorporating this learning in the closed loop. So you act, you observe an observation, you update your controller, and then you act again. So all the data is basically thrown away. However, if you want to be data efficient, then the key insight here is that all the data that you see is precious, and all the data that you have is actually true. So these transitions that you were seeing during controlling, you should rather store them in a transition memory and then make use out of this information at once. So basically, the first step is here to infer this knowledge in off-policy learning way, and NFQ, neural fit queue iteration, was one of the first algorithms that exploited this kind of methodology. And then once you store all the data there, then the second important step is how to collect the right data. So usually in reinforcement learning, you try to fulfill your task. You kind of obey to the task that you want to fulfill, and have the controller do that as good as possible. But if you're thinking of that this part is done completely offline, then you can also completely detach the collection part, and then the question becomes different. So the question is, how do I collect the right transitions so that my final learning is as good as possible? So during learning, you do not want to only solve the task, but you want to collect the right transitions. And in addition, this kind of detaches the control part, the learning part, the control part from the learning part. So learning can be done completely offline, and you can use all the compute resource that you have. So it's basically something like dreaming. During the day you act, at night you make sense of all the data that you collected.
Can you please repeat that? During the day you act.
As
some kind of control, and then you're learning. Trying to learn from that.
Yeah, so it basically says that you have a current controller, you control your system, and all the thing that you do is you just store all the transitions in your memory, yeah? And then you control just continues. So you're acting in the real world. You do something. In the background, some learners look at your memory and try to make sense out of that. Try to extract the information, and then provide new policies, new skills, and then at some point they are fed back to the controller, and the controller behaves differently.
Because you can't do learning online, or why?
It's just a switch in viewpoint. So basically to detach the learning part from the collection part, and this will give some advantage.
Why do learning online as you hope?
It allows you to do more computationally expensive learning, because
That's what I was asking.
Yeah.
People like Peter Stone did this before deep neural networks, things like Text Explorer, where they would have one parallel track of doing like model building, etc. You always need to have a policy available, so it chimes up.
Yeah.
It's the same sort of thing.
Yeah, it's the same sort of thing, and it also makes clear that for the actual the part of the controller during the learning is basically to collect the most valuable examples that help you to support the learning as good as possible.
So how do you collect? This is where I'm stuck. What's the right transitions, and how do you collect the right data?
I will come to that in a moment.
I think you collect all.
Yeah, you collect all, but you better. The thing here is you're looking for policies that concentrate on collection rather than on just performing your task. That's the kind of also a slightly different viewpoint than classical reinforcement learning. Okay, so you have basically two questions: how to squeeze out the most information of your transition memory, and how to collect the data. And I will quickly go through both. of them. So the infer part is the first one. As I mentioned, neural fitted queue iteration was one of the first algorithms that make use of this idea of learning from a complete batch. So you would approximate the queue function by a neural network, and then you iteratively minimize this queue learning rule based on dynamic programming. And this turns reinforcement learning basically in a series of supervised problems that you kind of could solve effectively. And my personal experience on that was, in contrast to these online TD updates from the classical reinforcement learning, where I needed more than 1 million episodes during my PhD thesis, with the NFQ this reduced to less than 300. And this makes it now out of a sudden possible to apply these methods directly to systems. Like in this case, the card pole system, where it learns completely from scratch, so there are no dynamics put into the learning system. It's just collecting the data, applying neural fitted queue iteration in the background, coming up with a new policy, applying this again to the plant, and after about 250 trials, it finally came up with a policy that learns to balance the pole upright. What's a trial? It's about 10 seconds of applying random actions. And the actions in this case are pure voltages. So it's really, we treat the whole dynamical system as a black box. So you directly go from actions to...
Have you tried running it more to see if you can actually get it to stabilize?
In this case, not. I think getting it to stabilize would probably require a richer state representation. So more information about the actual state.
So one of the challenges we've observed with these methods, even though they can be really sample efficient, is the maximization bias. So like join and precup and other way to deal with the max. I was curious in these results if you needed to do it.
So in this case, we didn't. But in the future exams, we kind of take also care for these kind of things. Okay, and there are a couple of more examples. So one was learning to drive on the Stanford car. We applied this to learning to dribble in RoboCup, so learning to handle the ball if you can't grasp the ball, but you only can do it by a clever driving. That's a pretty challenging problem. And the policy that was learned was much better than everything we came up in a couple of years of manual development. And in 2009, finally, this was one of the first examples where we directly learned from pixels to drive a slot car, where the signal was only to drive as fast as possible with a constraint not to fall out of the track.
Where's the pixels there?
Sorry?
Where are the pixels?
So we have a camera. So the only thing that we observe here is actually a camera where's the camera? I think it was above. So the camera is basically from above. Yeah, it's from, in this case it's actually above, so it's not shown in the video. Yeah, it's from above camera.
So what happens if you change the track?
then the thing would completely fail. That's a very good question, because in this case it relies on this one tracks, so there's no force or there's no pressure to actually generalize. One way would be to actually train it on many different tracks and also have it during training so that it learns, or to kind of force it.
Try to train them for transitions, you know, because what I'm saying is you train for one track, another track, but how if you're switching from one to another?
No, in this case we only had one track.
No, but I'm asking, have you tried?
We can try, yeah, sure.
But you haven't tried yet?
We haven't tried yet, yeah. So there's a whole history of these memory-based model-free RL algorithms. So one thing was NFQCA that I developed with one of my PhD students, Roland Hafner, to go to continuous actions. Then DQN was based on this idea, extending the idea of NFQ to mini batches for the Atari case, where you have large sets of training data with also convolutional layers to directly go from pixels. DDPG is kind of a version of NFQCA, again, for huge transition sets. SVG is for stochastic policies of soft actor critics, are for stochastic policies with constraints, and the methods that we are currently using is MPO, maximum a posteriori policy optimization, that we suggested 2 years ago, where the idea is, instead of using the gradients to update the policy, we have a sample-based strategy where we sample from our current action, weighted with the current Q function, and then based on the results of the pixels, of the samples, we move the new policy and learn the new policy in a parameterized way to be closer or to be better with respect to the current Q function. Q-learning works as before, but this method actually turned out to be much more robust towards hyperparameter selection. And here's an example. So we have an action space of 22 degrees of freedom. State dimension is more than 500. In 2017, we used about 128 actors and several days to learn this. And with MPO, we have one actor, one learner, and can solve it in less than 2 days. And you see it's also pretty robust with respect to the initialization of the policies at the beginning of learning.
What is an actor in this context?
An actor? That's the actual controller. So, yeah. And 128 actors means that what you can also do in simulation, you can run 128 simulations in parallel, collect a lot of data, and thus have a parallel learning and learn much faster. And in 2 years ago or 3 years ago, this was needed to get this to run. And now with the better methods, we could reduce data efficiency, or we could improve data efficiency considerably.
Do you mind just explaining a little bit these graphs? What do you mean?
So this is DDPG. This is one standard method that just flat lines. Then this is another learning algorithm, SVG, plus an entropy term that doesn't get to the high average reward. And finally, the MPO very quickly gets to a very high reward and therefore solves the problem. So the higher the reward, the more you're actually running. In this.
How do you define reliability?
This one is the reliability with respect to the initialization of the neural networks at the beginning. So for some learning algorithms, it's kind of, if you start them 5 times, then some of them flatline, some of them go up. And for MPO, it turned out to be pretty robust. So for no matter how we started, with what guess of initial policy we started, it always got to good results. Or robustness, yeah, with respect to the learning.
But reliability is the term that
in this case, yeah.
Reliability, you have the optimizer. The optimizer may fail or may not fail.
Yeah.
In this case, it doesn't fail.
Yeah, I think robustness is also kind of used in different ways. Therefore, we chose reliability, but it's not for now. Yeah. Okay, so this is one aspect. So the infer part. If you were given a set of transitions, how good is your algorithm that takes out the knowledge out of this set of transitions? And the other question is how to actually collect the data. I think in these cases, it's very difficult to say how good to optimality you are. I think this you can only actually evaluate if you have a system that you know where the optimal actually lies. So it's some very simple systems, and we have also systems in this respect in the control suite. For the systems like the humanoid, we can only say this is the best reward that we so far saw. And it kind of runs quickly, but in these cases you never know if you actually reached the optimum or if it could still be improved. And then it's also in simulation. So if your simulation has some flaws or something like that, then you can get to a higher reward or to a lower reward. So it's very difficult to judge whether we actually are at the optimum. The only thing that we can say is that we are much better than before.
So did you have some examples where you knew what's optimal and then you tried to learn from that and then use that a priori information?
Yeah, as I said, for simple dynamical systems, you can compute what the optimal is, optimal timers or optimal time controllers or something like that, and then you can compare against. But when very often you are very close to that.
Is there a way to extrapolate that? Okay, so simpler dynamics, you do something that you learn from optimal. Then you have a system where you don't know what optimal is.
Yeah.
But try to use a similar approach.
In principle, yes. Yeah, it depends. If the system is so complicated, then you cannot solve it analytically, and there's no analytical solution known yet by classical control. Then it's very hard to say where the optimal actually lies.
I'm trying to see if you have had some experiments or exercises or whatever, where you actually try to do it on a smaller system and then enlarge the scale of the system where you cannot find analytically the optimal.
Okay.
But use what you inferred from the smaller size.
Yeah.
Behavior speed. There's a new environment class that you can scale the environment. You can compute what's optimal up to a certain amount, and then from there you can get the scaling curves that show you how you're scaling.
And how is that called?
Behavior speed.
Mm-hmm.
It's on GitHub.
Okay. So the second part of collect and infer is to collect the right data. And there the question is, as I told you before, if you have a large search space, large search tree, and the reward is only sparse, how do you get ever there? So how do you detect that once you stacked an object, or even you grasped an object with a random robot movement, it's very unlikely that you actually see this. And so the idea is that humans learn to activate their senses deliberately. So that's these are kind of auxiliary tasks that finally leads to more and more complex behaviors. And why don't we do the same with our robots? So if you have a state space, if you would do random exploration, you would always stay very close to the initial state. And if the goal is far away, it's very unlikely that you ever hit it. But if you have a set of auxiliary tasks that you potentially can reach, and from one auxiliary task you can probably build something else and get to something new, then you finally also have a chance to finally reach the goal. And that's the idea of scheduled auxiliary control, where you basically have instead of a single reward, you have a whole vector of rewards. Every intention is executed during learning. All the intentions, they share their data in this transition memory. Again, this idea of having a transition memory where you infer your knowledge from, and then you can learn all the intentions in parallel by these learners that access this transition memory and learn their value function and their policies according to their respective reward function. And what you can do, moreover, you can both just randomly activate these skills while collecting, but you can also have some meta learning there. Once you've seen, oh, there's some new reward and this looks interesting, you can schedule this intention more often in order to speed up the learning process. And this is an example where a better collection process might overall lead to better data efficiency. Yeah, exactly. The advantage against reward shaping, if you do a reward shaping, if you do it wrong, then you kind of never will get to the solution. Here, the only thing would be that you collect data in a part of the state space that is potentially not interesting for learning on. But it wouldn't harm your final policy. And that's kind of the... It could slow down learning, yes. If you have a lot of intentions that do not help you, then it could slow down learning. On the other side, if you have a good scheduler that finally takes, oh, if I want to do stacking, then I better grasp something and go on from there instead of just randomly wiggling around over here, then the scheduler could decide, don't call this intention too often where you just wiggle around. So that's the idea of the scheduler. Okay? So and here's an example. So we have a 9 degree of freedom continuous action space of a robot arm. We have 15 sparse auxiliary rewards. So they're only giving rewards if actually something happens. So for example, if an object is moved, or if something is touched, so if the touch sensor is on, goes on and off of the gripper, if an object is left of each other or right of each other, their intentions to exactly do this, or if they are somehow above each other or close. And then we have also 6 extrinsic rewards. These are the final task rewards that someone actually asks or demands from the final robot. And so here you see an untrained system, an untrained robot arm, because it has so many degrees of freedom, it would just do random movements. But then after some time, it actually started to touch objects and moves the objects. And once it found that it occasionally does this, it deliberately wants to actually call the intentions that do those. And after some times, these intentions are actually learned. So at this stage, the robot, whenever the intention move object is called, it actually goes towards an object and gets reward by moving the object. Then later on, it has also learned to put the object left and right, so attaining some relationship between the objects by grasping them, by putting them somewhere. And yeah?
Are these intentions pre-programmed or?
No, they are always learned. So only the rewards are given.
Okay.
So you.
No. So what I meant is that the reward functions for these different subtasks.
They are given.
They are given.
Yeah, exactly.
That was my question.
Yeah, and they are given with the thing in mind what could be potentially interesting in this domain. For example,
so
relation between objects, moving objects.
So is it fair to say that you have a task decomposition in your mind, which
yeah.
you express in terms of reward functions,
absolutely,
and the rest has to be filled out with learning?
Exactly. Yeah, that would be an engineering way to do it. In a very general setting, you would come up with many reward functions, like 1,000 or so, and having a good scheduler that only schedules the interesting ones to get more and more interesting rewards.
So you sort of have a language reward function.
Yeah, exactly. Yeah. And so this is then the final policy where the ARM has to clean up the table by first lifting the lid of the box and then putting the objects inside. And you see it has learned this pretty nicely with this scheduled controller. And also, for example, if the objects are stacked, then it comes up with a very efficient policy to take both objects and put them to the lid at once. So it's because everything is basically optimized for time. Yeah?
This is like a completely sincere question. So, like how, it seems like how do you square this with what you were saying at the beginning about like general and like general intelligence and like from scratch? Like it just doesn't seem like this is.
So it's from scratch in the sense that we have no idea how to actually do this. So this knowledge how to actually control it is not put in. The only thing that we are giving in this case are auxiliary rewards and the rewards what we finally want to achieve. But the policy, how it ever should reach something, that is not, this kind of knowledge is not in there.
Okay, so it's
and
the dynamics of the robot.
Exactly, yeah. And in that respect, it's completely model-free, and there's no classical control knowledge put into this approach. To push it even further, but it's a very good question, to push it even further, the interesting question would be, if we even don't give the reward functions, is there some mechanism that generates interesting reward functions? Because then the mechanism to make sense out of them and to learn data efficiently from there, that's already there. That's given with this SAC X approach. And so we could push the boundary, and that's actually what we're currently trying to think about. How can we get rid of our definition of reward functions?
Okay, thank you.
You're welcome.
What is the architecture of actors actually? Like, how many layers, what kind of neural networks are you using?
Oh, that's a good question. I think it's in my honest answer, it's in the paper. there are several layers. I think if we learn this from pixels, then there's also a convolutional layer that does all the pixel preparation. And if it's learned from features, then it's kind of a 3 or 4 layer networks until we get to the Q functions. And in this case, what I can say definitely is that the intentions all share some common layers, basically to make sense of the environment, and then they have their heads where they specialize on their particular rewards.
Stupid question. How many layers is good enough? How do you decide on that?
When it starts to learn and gets to a good performance. So it's still solved only empirically. So there's no analytical answer to that. Yeah, the only thing that we are striving, and that's what we're striving for, is to have some kind of standard architecture that solves a very broad range of tasks. But that's also found by just searching through the space of different networks.
Can you give an order of magnitude of the number of layers for the people outside of the domain? 10, 100, 1000?
No. I think it's rather in the range of 10-ish. If we have convolutional layers, if we learn from features, then it's even lower. Then it's probably 3 or 4 hidden layers, and then going to the Q functions.
So that's what you're seeing, 3 to 4 layers.
If you already have come from pixels to features, then 3 or 4 layers to learn the rest. That's good enough. If you need to learn from pixels, then you probably also have convolutional layers, which can be also in the range of 5 to 10. To get from the pixels to a kind of condensed representation. Okay, and so generality, so we can apply the same agent with the same auxiliary rewards and learn a completely different kind of hand. So it's a simulation of a shadow hand. And we can also, of course, learn to deal with different objects that have different physics. So stacking a banana on a banana or stacking with a banana is, of course, something different than only stacking blocks, because then you also have to learn something about the physics of the banana if an object is stacked or not. Yeah?
You need to retrain those models using simulators.
Yeah. Yeah. In this case, for these domains, a new agent is learned with a new network. But it could also be that, for example, you expose the same agent to a whole set of different objects, and then you would expect that it learns for every object kind of a slightly different handling structure. Yeah?
For these different tasks, is there kind of like a different distribution of time that it takes for each task to be learned, depending on its content?
It's roughly in the same ballpark.
So there's like a large variance. Generally, there's some time point when all these simulations learn to do that task, or is it relatively spread out?
So it's roughly, yeah, as I said, it's roughly in the same ballpark when they are kind of converge. Okay, and it can also be applied to more classical control domains, like this double card pole, where one agent learns to control the system at all stable points. Okay, so as an intermediate summary, so this is the basic principle that we have, this collect and infer, so to take care of methods that do a proper collection of data, or they are kind of solve the exploration problems. On the other side, methods that are very efficient in extracting all the control knowledge that is in the transition data. And there are a couple of research directions where I want to give you a quick insight in the following slides, like improving efficiency through better exploration or richer policy classes, by using models to help either with learning or with exploration. Then some point that has already been brought up, how can we learn even with less prior knowledge, so learning the reward functions also, or learning from pixels, getting to raw input spaces. And then also extending application cases, for example, learning from pre-recorded batches of data. That was a point that was also mentioned yesterday. So one
one direction is the use of learned models, and you can do it both on the actor side. So, for example, using methods close to model predictive control by learning a model. In this case, in the embed to control case, we forced the system to learn a linear transition function by mapping inputs to a respective high-dimensional space, and then we're able to learn to derive a control law based on the knowledge of these linear transition functions, or the linear matrices in the core of the prediction model. So this is an example where learning a model helps on the actor side, but there are also examples for learning that helps on the learner side. Learning a model that helps on the learner side. And one example is IVG, imagined value gradients, where you learn a model in order to propagate the information that you get from the future better to your current policy. And so this is an example of how a typical model would look like. So here are the observations. So the x0 are images, p0 are proprioception in the robotic example. And since these are only observations and don't make up for the state yet, we're using LSTMs to come up with a state estimation. Then the state estimation gets with the action to a successor state. And from the successor state, we either can go to the next state with the next action and so on, and predict the future of states. But for every state also we can predict the reward and the value function. And at the same time also decode the next image. That's the idea of predicting what's actually happened also in image space. So this is the way how usually these models are set up. And then what we can do, so this policy that now depends on the internally estimated state of the system and gets an action. And then we can propagate the values back in order to update this policy instead of only using the TD error as it would be in classical reinforcement learning. So we can use whole rollouts, and this improves the estimation of the gradient drastically, and therefore also finally improves learning. So this would be without a model, when the learning performance is good enough without a model. And you see the stacking curve, for example, the red curve here, it lifts up much earlier because the model helps to improve the learning drastically. Other ways are we can use other policy representations. So the approach allows also for having both discrete and continuous actions in the same way. So we can have mixed policies that both have a discrete components and continuous components. And one toy example is this, where basically we have a discrete component that first selects which part of the high-dimensional action is actually influenced, and then a second continuous controller that actually puts out the actions. And then you see for walking, for example, because it cannot at the same time influence all the actions, it has to decide which joint or which joint to move next. It learns a very special gait, and in the case of the swimmer, it actually learns to move the joints accordingly, so that actually a swimming movement is finally observed. And a more serious application would be that of a coarse and fine controller. In this case, the question is how to insert it. And outside, if you're far away, you could move faster. If you're closer, you should move with smaller actions. And in this case, the agent actually learns when to select the coarse mode and when to select the fine mode. And it also learns the policy for these respective modes, so that finally the tasks can be solved accordingly on the real robot. So I think I will in the interest of time, I will skip this. I will just show that this can then also be applied to solve challenging real-world task with the robot. Again, this is learned from scratch, and we can now also learn it directly from pixels. The
question is how to actually stack one brick on the other. And for us, it kind of looks like a simple task. But remember, the robot first has to learn how to grasp an object, to grasp this brick, right, to close the fingers, then to move to the other object. And then it's also not always possible to stack it directly. But as you see, it has also learned to first bring the lower brick in the right position and then uses the other brick to actually stack it. And here it uses a different policy. And so in the final video, because we were talking about dynamical systems that are directly trained from pixels. So we recently managed to learn the ball in cup problem directly from scratch from pixels. So we have the ball can move in 3-dimensional space. The only actions are 4 raw actions, so it can move 4 joints of this robot arm. We have 2 cameras because the ball can move in 3-dimensional space. And these 2 cameras are the only input, giving idea of the state. In this case, we have a couple of auxiliary rewards, like I defined before in the learning by playing. And you see at the beginning, the robot has quite a hard time to kind of catch the ball. But this happens after about 80,000 episodes. It finally learned how to reliably catch the ball. And again, the stick that Russ mentioned before is used to disturb the robot. So it's actually a closed loop policy. And on the left side, you see the input of which the robot has to make sense in order to solve this problem. Okay, and if you hide one camera, of course, then it cannot solve the task. Only if it has the full information that it was getting for learning, it can eventually solve the task successfully. Okay, and with that, I'm at the end of my talk. So to conclude, we are aiming at the far end of learning control, which we called artificial general control intelligence, where we finally want to bring in a minimum set of maximal generally priors to learn a wide variety of tasks without a lot of human inputs. Ideally from raw inputs with raw outputs with a pure task specification and still data efficient. So that's kind of the area where we're working on. Guided by our principle of collect and infer, we can go surprisingly far. So these methods scale relatively well to even high-dimensional action and state spaces. What we also observe, the less that we put in a priori, the more creative the solution gets. So this is similar to our experience with AlphaZero. And also Sutton's recent paper on bitter lessons kind of refers to this fact. And on my wish list, what we need to do in order to be actually kind of competitive to classical control theory, we need reliability of these controllers. So it should not only be that we show these learning curves, but we should also have some proofs that in any situations they do something useful. Kind of interpretability of these controllers would be nice. What we need as a community, I think, are sound benchmarks together with the control community so that we actually can do a comparison to classical control. And with that, I conclude, and thanks for all your questions already through the talk.